Hello, everyone. Today we will talk about the 90 degrees and 180 degrees RF pulses in MRI sequences. There are different forms of pulses in MRI sequences, and the 90 degree and 180 degree RF pulses are two pulses that are very commonly used and very important. It is necessary for us to understand them separately. First of all, let's see that on our EDU-MR, the sample is placed vertically into the probe. This one below corresponds to our internal diagram of the device. The magnetic field is oriented from the left to right. After putting in the sample in the magnetic field produces a magnetization vector, which we also call the longitudinal magnetization, denoted by M0, and it is oriented along the main magnetic field direction. We plot it on the coordinates, and M0 is along the z-axis direction. At this time, we apply a 90-degree IF pulse. Then the longitudinal magnetization vector will be deflected by 90 degrees to form a transverse magnetization vector in the xy plane, denoted by MXY. After the pulse ends, the transverse magnetization vector cuts the probe and produces an NMR signal. The instrument then measures an NMR signal. This is the case of a 90-degree RF pulse. Then let's look at a 180-degree RF pulse. After the longitudinal magnetization vector is generated by the sample, we apply a 180 degrees. This deflection angle can be calculated based on the intensity and duration of the IF pulse, which corresponds to this equation. This is the deflection angle. Gamma is the gyromagnetic ratio. B1 is the magnetic field generated by the IF pulse, and T is the duration of the RF pulse. If the intensity of 90-degree pulse and 180-degree pulse are the same, the duration of 180-degree pulse should be twice as long as 90-degree pulse, and the duration of 90-degree pulse is T. And the longitudinal magnetization, the duration of 180-degree IF pulse should be double T. After the 180 degrees, the longitudinal magnetization vector is deflected to minus M0, and there is no transverse magnetization vector at this time. So the NMR signal is not detected at this time. The 90-degree and 180-degree pulses were introduced separately earlier. Now we learn about the combination of 90-degree pulse and 180-degree pulse. For example, the case of adding 90 degrees after by 180 degrees. The 90-degree pulse is exactly the same as the one described earlier. After the 90 degrees pulse, the transverse magnetization vector is generated, allowing us to detect the NMR signal afterwards. After the 90 degrees pulse, the longitudinal magnetization vector recovers from the zero and the transverse and the transverse magnetization vector decays from the maximum. If a short period of the time after, let's say 5 milliseconds, the magnetization vector will recover from zero. After 5 milliseconds, the magnetization vector is such that the longitudinal magnetization vector is partially recovered, but very little is recovered. A small arrow is drawn on the graph. After 5 milliseconds, the transverse magnetization vector also decays partly, and the amount of this decay is sample dependent. Now let's apply a 180-degree pulse. At this time, the recovered longitudinal magnetization vector is deflected by 180 degrees to the z-axis. The remaining transverse magnetization vector will also be deflected 180 degrees to the x-axis. At this point, we can detect the NMR signal. If the detection timing is right, an echo signal will be detected. The time sequence of this pulse corresponds to our spin echo sequence. Let's look at the sequence diagram. After a 90-degree pulse, if we acquire the signal, we will detect a FID signal. After 180 degrees, we can acquire an echo signal. Why can an echo signal be collected after 180 degrees? We will explain this further later when we introduce the spin echo experiment. Now let's look at another case when a 180-degree pulse is added first, followed by 90 degrees pulse. The first 180-degree pulse is the same as the previous one. After the 180 degrees pulse, the longitudinal magnetization vector the M0 is deflected to the minus z axis, forming a reverse magnetization vector, and the coil cannot detect the NMR signal at the time. After the 180 degrees pulse, after a period of time, the longitudinal magnetization vector recovers from minus M0 and the transverse magnetization vector is 0. At this time, we apply another 90-degree IF pulse. Then the negative magnetization is deflected by 90 degrees to form the transverse magnetization vector. At this point, we can detect a FID signal. The sequence of adding 180 degrees and then 90 degrees corresponds to our inversion recovery sequence. We also call it IR sequence, and this is the sequence diagram. This IR sequence will be described later when we talk about the T1 relaxation time. So that's all for today's talking. We will share the video of the software operation later. Thank you.